pleasure to be here. And as Sam said, I will talk about two different subjects. The first is joint work with my student Itai Evron, postdoc Edward Moroshko, and collaborators Rachel Ward and Nati Cerebro. And we're asking how catastrophic can catastrophic forgetting be in linear regression. Okay, so this will be the first part of two-part talk. So if you don't understand something in this part, you can always, I'll remind you to wake up so you can maybe understand in the next part. Okay, so let's start. So what is catastrophic forgetting or continual learning? Let's try to explain the setting. So we have tasks that arrive sequentially, each with its own distribution. For example, we have an autonomous car, and you want to train the car, and you see the car sees some settings in the morning, and then in the evening, and then in the night. Each time you might drive to a different country, and you want to continuously train this car to learn on all those different environments and times. So the goal is that we learn the model on all the tasks together. So we perform jointly on all tasks together, even though we train sequentially. So what is the problem? One major problem is forgetting. When we learn new tasks, we might forget the previous task we've learned. So this is a nice picture from Couture et al. That shows this, that when we learn one task, we have these two clusters we want to separate. We learn some decision boundary, and then we learn a new task. What ideally we'd like to do is to retain the decision boundary on the previous task, but still have good performance on the new task we've learned. So what happens in practice that there's no reason when we learn the new task, unless we do something, there's no reason that the boundary will still be good on the previous task. So it kind of changes because of the training procedure or the implicit bias of the algorithm, and then we get bad performance on the first task. So that's we want to prevent this forgetting or catastrophic forgetting, meaning it's a very bad forgetting. So a common research goal in this area is finding all kinds of algorithmic approaches and methods to overcome forgetting and try to decrease it. However, I'm trying to focus on this more basic question: why do we actually have forgetting? What is the reasons behind this? Does it always happen? And can we say in what setting it occurs? So this basic question seems to be unclear even in the simplest setting. So what is the simplest settings? As usual, we start with gradient descent, or SGD, on linear regression, right? It's the simplest model. You can try and answer things and try to answer those questions here. So just to, what are the main questions we're trying to understand? First, can forgetting become catastrophic? Meaning we can fit all the tasks, even in this simple, very basic model. So as a spoiler, the answer is yes. Even in a very simple model, we can get catastrophic forgetting. Next, is there a way to prevent this forgetting in this simple model? Well, the answer is yes. We can do various things. For example, we can repeat the task, just show the task again after some time, or just randomize the order of the task. Both things will prevent this issue of catastrophic forgetting and will show we guarantee to converge to a solution without forgetting. And lastly, how does the task similarity affect forgetting? So if we have two tasks and we want to remember both of them, is it better to have similar tasks or different tasks? So there was already previous theoretical work trying to answer this question. For example, Duan et al. In a linear regression model claimed that with high task similarity, you obtain the maximal forgetting. So if you have very similar tasks, you have the worst case. You don't want to have similar tasks. Another work in a different setting claimed something different, that you have intermediate task similarity causing your worst case forgetting. So even though it's a different model, this seems to be a conflicting conclusion, was kind of confusing. So what we find, at least in the linear regression case, that both actually can be true. It just depends on the number of tasks you've seen. So it can be also high task similarity or intermediate. This will be one of our conclusions. Okay, so this is the take-home message in case you fall asleep in the rest of the talk and this part. So let's go into the details. In our setting, we again use continual linear regression, meaning we observe a sequence of tasks, x1 and it's labeled y1, until y1 until xt and yt. And then we learn a linear model sequentially to want it to succeed on all tasks at the same time. And the task we assume, like it's common in deep learning, we always can perfectly fit all the data together because we have sufficient capacity. So here also there exists at least one model, W star, which can fit all the tasks at the same time. So they're jointly realizable. And we just use the simplest fitting procedure, vanilla gradient descent or SGD, meaning we initialize first at 0, and then at each iteration, each task we see, starting from the previous solution, we minimize our loss, just square loss for linear regression, either with SGD or gradient descent until convergence. And then we set the initialization to the next task as the solution to the previous task, and then repeat over and over again. Okay, and the final output of the algorithm will be the last solution we find when we fit to the last task. Okay, so just to define some quantities of interest, what we might be interested of. So suppose there is some offline solution which we can get by fitting all the tasks together. What will be the distance over the solution we get during the task? Distance for that solution to the best solution, this offline solution. So this is one thing we want to know, to understand. And the second thing is forgetting. So what is forgetting? It means what is our prediction on the previous task in comparison to what was the best prediction, like what was the error of our, if we've done optimally on the task, they just predicted the correct label, in comparison to what we predict now after we've seen all the tasks, like how much we forgot since we saw that task. So when we average this on all over the task. So this was a common definition in previous work. Also like Doan et al. So just to small note, this is a bit similar to regret, but it's not regret. Okay, I'll leave it to you to make sure it's something different, and it behaves quite differently from regret. So what can we say here? So just mathematically, because it's linear regression, we solved with SGD, we know that the solution we converge to is a very specific, unique solution. This is the mean norm solution, which can get a closed form formula. You can see it here in the bottom. And now we can start from this point and say what do we get when each time we just get this WK using the solution of the minimum norm. So we can express this in a slightly more intuitive geometric way. Just rewrite the equation and say that each time we're going through a task, what happens is the distance or the difference between the solution to the task to the optimal offline solution, this difference is actually multiplied by some projection metrics. So each time we fit using linear regression, we are actually projecting to a new subspace, which is determined by the new task. Okay, so we have some solution space where we're at, which is the difference from our solution to the optimal teacher, and each time we're getting to a new task, we simply project using this matrix, and get this new solution here. And that's kind of a way to show it. Now, if we do multiple tasks, we just do a product of these projections. Okay, so you can now move from this task of continual learning to just repeated projection. So we formulate this mathematically. Okay, so now again, if we have this final another task, we do another projection until we get to the end. And so it seems that when we learn each task, we contract the distance to the offline solution, right? Each projection is cannot expand; it can only contract or keep things the same. So intuitively, it seems maybe if we just do more tasks, we should converge to the offline solution. Okay, we're kind of monotonically decreasing in our distance to the teacher, to this W star, so we should eventually converge, right? But yeah, if we monotonically decrease, but we not necessarily decrease at a constant rate, we might get stuck at some point. So the question is, do we actually converge? And then another quantity we defined, the forgetting, how can we look on this geometrically in our problem? So the forgetting is just, if you write the expression you had before, you can see it's the sum of these projections, the other orthogonal projections, the complementary projections on all the tasks. And you can just visualize this as the distance between the last, where you are, to all the sum of all those projections back to the previous tasks. Okay, so now we have an expression for the forgetting and distance for the teacher using these projections. The question is now, what can we say mathematically? Some results. So the first question was, can we get catastrophic forgetting? Is it possible to get that we don't converge it all to the teacher? And the answer is yes. So we can construct a series of tasks so that we're arbitrarily bad in terms of forgetting, meaning the distance to the teacher and the forgetting both are bounded by some constant which can go to 1 arbitrarily bad as t goes to infinity. So the intuition behind this example is that we do very small projections in the beginning, so we maintain a constant distance from the W star. We don't really contract so much. And then we do larger contractions in the end, and we get a high forgetting. If we sum all those differences, in the end, we get pretty large forgetting. So we can be arbitrarily bad if we do get such types of tasks. Okay, now the question, can this be prevented? We don't want to get a high forgetting. So let's look at some setting where we can show it's preventable. So one setting, for example, is a cyclical setting. In some cases, tasks occur in some natural order. For example, I mentioned the time or the day, so morning, afternoon, and then evening. Then you get some repetition in the task. You sometimes see the task again. What happens in this case? Again, each task has a corresponding projector, P1, P2, P3, and then we see a P1, P2, P3 again. So we can just write this series of projection as a cyclic operator, which is we simply take some projections, take the product, and then to the power of n, the number of times we see those set of tasks. Okay, so in this setting it's a well-known field. It's called the alternating projection. It was studied since maybe von Neumann in 49 or the 60s later. So there are a lot of results in this area. So let's see if this helps us. Let's look at the simplest case. So the simplest case is, say, we have 2 tasks, and we want to just repeat between the tasks, go back and forth. What happens? So we have task 1, and then we project to task 2, and then we project back to task 1, task 2, and so forth, until if we do it enough time, like we see that we will converge to this teacher, the best solution. So you can show mathematically that after n cycles, if you do this alternating projection, you can find the rate of convergence. And just using, here we assume that the teacher has some, without loss of generality, it has some scale. So if we use this scale, we can write this as just this norm of the projection matrices. And then we can bound this using standard result from alternating projection. And we get this is a function of the angle between the subspaces. Okay, so here in this 2D example, it's very easy to visualize this angle. But more generally, it's the smallest principal angle between the tasks. Okay, so when you have a small angle here, this is bad, because this will converge very slowly. We'll have small angle, the cosine will be close to 1, and we'll have very slow convergence to the teacher. So essentially, it could be arbitrarily slow. If we have the worst case task, then still forgetting can go very slowly to 0, which is bad. So this is distance to the teacher, sorry. So distance to the teacher can be arbitrarily slow convergence. So, right, because again, if you have this, if you have this very small angle between the tasks, then you do very slow convergence. So what about forgetting? So we talked about distant teacher. However, forgetting has a more favorable behavior. If you write forgetting for this analysis, which was actually, this part was not explored in the alternating projection literature. This was kind of novel. We get a different expression where we have this 1 minus cosine times this cosine to the power of the number of tasks. And now this expression is actually upper bounded universally. This is all the principal angles, and you can upper bound it universally with this decaying function as a function of n. Okay, 1 over 4 en. So it doesn't matter which angle you use, you know the forgetting will always converge to 0 with this upper bound. Okay? So this is actually a sharp upper bound. You can show lower bounds. So what do I mean by sharp? So it's not tight, because for every n, you will decrease exponentially, right? It makes sense. You do alternate operation, you have decrease exponentially, but you can go a very slow rate. However, this sharp upper bound determines that you can't get eventually slower than this power law. Okay, so you can get very slow exponent, but the power law is upper bounding all those exponents. Okay, so that's kind of a nice universal behavior we get here for t equal 2. And what happens if we don't do repetitions? We just do 2 tasks. Okay, so we have n equals, here n equals 1, and we have this expression. So what can we say about just 2 tasks? So if we look at this expression, we know that if the angle is 0 or pi over 2, meaning the tasks are identical or orthogonal, then we get 0 forgetting. So that's the good situation. Exact similarity or exact orthogonality are the best cases. What is the worst case? So if you look on the worst case, it's actually the middle here. It's the angle 45. So this is for 1, if we don't do any repetition, n equals 1. So we see that if we don't do any repetition for 2 tasks, we get the worst case, the maximal forgetting, and what is when both tasks have intermediate similarity. They're not exactly the same and they're not orthogonal, there's something exactly in the middle. However, if we increase the number of repetitions, we get that the maximum point of this expression is actually getting smaller and smaller. So if we see a task a lot of times, we actually get that the worst case is in a high similarity. So very similar task will actually converge slower. Okay, so this kind of reconciles previous observations and results in the literature. Okay, what about the general case, more than 2 tasks? So there we can derive a bound, again, the universal bound, which depends on the number of tasks, the number of repetitions, and we can either have a dimensionless bound, which has worse dependence on n and t, and with dimension we can get a better dependence on t and n. So we think it probably could be improved. It's hard for the last iterate analysis, but with averaging you can get around t over n. So you can, for some setting, you get better performance. Another case you can prove a bound, again for general number of tasks, is if you do random ordering, stochastic ordering, not cyclic ordering, with or without replacement. So this means that in that case, we look at the average forgetting over this random ordering of a task, and we see that it behaves as 9 over d to 9 of d over k. So again, if you do averaging, you can get rid of this dimension constant. Okay, so in this case, actually, if we do, you can prove it for both if, with, and without replacement. So without replacement case tells us that because this does not depend on, because this does not depend on t, it means that we can actually show an infinite number of tasks at random order, and it will still be, you get forgetting going to 0. So you don't need to repeat the task, you just need to show them at random order. So this is also showing that this random order claim. Okay, so how is this relevant for practice? So this is, for example, a recent paper scaling the number of tasks in continual learning that showed that actually if you do use task repetition, you don't have much forgetting. So what they did there, they chose 2 classes. I think it's from CFAR, 2 classes from CFAR. Each task is 2 classes. And then these are the different tasks, and then the test set was on all the classes together. And they use vanilla SGD to train the network. And if you just repeat the task, they have a lot of tasks. I think here it's MNIST, but they also have CFAR 100. And if you do this repeatedly, you actually get convergence to pretty good accuracy. So it seems that repetition indeed prevents forgetting. So it was kind of nice, and also 2 previous work that showed that. Okay, just to summarize this first half of the talk, generally we showed that even in linear regression, forgetting can be catastrophically bad. You might forget everything. And we quantified the exact effect of task similarity, how tasks should be similar to be good or bad in terms of forgetting. And we show that if you do cyclic or random ordering of a task, then forgetting diminishes linearly with the number of seen tasks. Also in the paper, we show other things we didn't mention here. What are the conditions for zero forgetting, which are more general than just the zero angle or orthogonal data. We have matching lower bounds. Well, not tight lower bounds. We have lower bounds. There's some gap there. And then we talk about the relations to other algorithms, catch-match method, alternating projection, stochastic proximal point algorithm, and many more. Okay? So, yes. Questions about this part? Yeah.
A couple of questions.
Yeah.
The first one is, in the realizability assumption,
yeah.
There is no reason to believe that the W star is unique.
Yes.
And all of your distances were distances to one W star. Shouldn't you have used a distance to the set of all global minimizers?
No, because this it's interesting. Because you do all your in gradient descent and SGD, all your iterates are lying on the manifold of the data. Okay, so it means that if you go over all the tasks, you can only converge to the minimum norm solution on all tasks together. So it is unique because it has, because of this property, it has to be the minimum norm solution.
Of implicit bias. Okay. The other question is, it seems that this is a problem of vanilla SGD more than the fact that forgetting is a general phenomena there. Namely, there are all of these techniques where you rather than just following the gradient, you project onto the space or the subspace corresponding to the previous tasks.
Yeah, there were previous methods like that.
And so isn't it the case that if you do that, then you don't need to do random, or you don't need to see new examples?
Yes, you don't need it, but there is a cost to that,
okay.
Right? You need to store the data in some ways. Like storing the data or projecting, it has pretty high cost.
Well, in general, maybe yes, because you need to store the data. But here, because it's linear regression, you just need to store a basis for the subspace.
Yes, but I think in practice, like in neural networks, people do that, and it has some limitations. Eventually, you run out of budget. You can't do that. I think also in linear regression, right? You need to store subspace times the number of tasks you saw. So that could be quite a lot.
No, because here there is just one subspace, right? At the end of the day, you're trying to intersect multiple subspaces. They're all linear. You're trying to find a solution W that is in the intersection of a collection of subspaces. And so every time you get a new task, you're just reducing the dimension of the intersection.
Intersection of the new task, I see. Yeah, I guess that could help. I think there are still some issues there in terms of, we can discuss this offline. Okay. Any more questions? Okay, so I'll keep going to the next part. Okay. So yeah, so the next part is about the implicit bias of minima stability. This is a joint work with Rotem Ulayev, Tom Michaeli, and this is the first work from NeurIPS. And also there's a continuing work with my student Mor Spiegel-Naxon and Greg Ongi, who joined in. It's under review about the implicit bias of minima stability in multivariate shallow ReLU networks. Okay. So the motivation here, we want to understand the behavior of neural networks in an over-parameterized regime. And as we know, given some data points, we can perfectly fit to those data points if we have sufficiently large network. However, there are many different solutions we can get. Okay, so the question is, which of those solutions do we converge to with our optimization algorithm? Okay, so this is the algorithmic bias, implicit bias, an inductive bias of the algorithm. So in gradient-based method, there was a conjecture already in 2017 that the implicit bias of the algorithm can be expressed as some form of regularization. And this was actually shown in many works, linear regression, matrix optimization, linear classification, separable data, and many nice examples. However, there is limitation. This does not always work, this analysis. For example, for a mean square loss, it was shown that to get this to work, you need to have some manifold property to hold, and does not always hold. And in some cases, it was shown that it fails. For example, Ohad Shamir and Galvardi had the paper, and also Razin and also here, and Cohen, Nadav Cohen showed this. And so this is one issue. And another issue is we do not capture the dependence of the step size. We don't know how the step size is affecting the results, because most of the results assume either gradient flow or small enough learning rate step size, so we're not much different than a gradient flow. So, however, the step size has quite a lot of impact on the performance and the function we get. So if we train a neural network with some small step size, so we see the loss function is decreasing, and we get a function that perfectly fits the data point, and this function is quite changing rapidly, like it's changing quite a lot. It has high frequencies or overfitting. However, if at some point we increase the learning rate, and then we train with this high learning rate, we see that the function we get in the end is much smoother, at least in this middle part. It's actually there's a large slope here in the end, but in the middle it's much smoother. So this seems like it's overfitting less. And also in practice, people use high learning rates to get better performance in terms of generalization. So it seems that high step size does get better performance. So it's maybe good practice to use high learning rates. So we want to understand this. And to do so, we use the property that SGD converges to stable minima, or gradient descent converges, and SGD goes to there maybe with some noise. And this property always holds. If you converge to a stable minimum, we have some property that has to hold. So we can use that property. So what do I mean by stable minimum? So we have different types of minima. We can have flat minimum or sharp minimum, minima. And if we use gradient descent or SGD on flat minima, then we can converge to the minimum. However, if we use the same learning rate on sharp minima, because of the dynamics optimization, it can escape exponentially fast. And so we call this a stable minimum, and the other one an unstable minimum. And so the condition for gradient descent to be stable is that the lambda max, the maximal eigenvalue of the Hessian, will be smaller than 2 over the step size. Okay, and if it's higher than 2 over the step size, then we're unstable, or we will escape exponentially fast. So for gradient descent, this is a necessary and sufficient condition, and for SGD, it's just a necessary condition. Okay, and then we'll use this condition to derive our results. So what do we show in this work? Just to summarize, first, the problem is that to use stability in ReLU networks is problematic because they're non-differentiable, right? So how can you use stability for non-differentiable minima? So we devise a framework for analyzing switching system, which is more complicated than just differentiable minima. And we show that with large step size, we do converge to a smoother function, like we saw in the results, meaning it's not only smooth, but smoother in the center of the training distribution, but not in the outside distribution. And we verified this behavior experimentally. So in this talk, I will focus about the two last parts, because the first part is more complicated to explain. Okay, so we focus first on the very simple case of a univariate shallow ReLU networks, meaning our input is scalar and the output is scalar. So we have first layer W1, B1, ReLU, W2, B2, and then we get a scalar again. So this is the function we have, the neural network, and we have a ReLU activation function. So we denote by this calligraphic F as the set of all functions of this type, all the ReLU functions. And for a given k, it's a piecewise linear function with k knots, k breaking points. And we train this using a quadratic loss, MSE loss, on a certain all data points. And we assume that we're in an over-parameterized regime, so the number of neurons larger than the number of data points. So we can get a small error and specifically get to 0 error, perfectly fit all the data points. In this case, there are infinitely many solutions, and I'm trying to see which solution are the one corresponding to stable minima. So to answer this question, we first had to answer some more basic question: how do you define the flatness of some function, so we say we converge to this function with a neural network, what is the flatness or the lambda max of the Hessian for this function? So it's not really clear because there are several implementations we can use for the ReLU networks to implement this function. One implementation can be flat and one implementation can be sharp. For example, if we just scale the layers, just multiply the first layer and the second layer by some constant, and we change them, we can change this sharpness quite arbitrarily. So there is some ambiguity, and the way we propose to solve this here in this case, we just, if we define the set of all parameter vectors that implement the same function as capital omega of f, then we focus about bounding the flattest implementation, meaning the set of parameters that have the flattest, the smallest lambda max of the Hessian, the least sharp. So we'll show why is this useful. Okay, so now I want to ask how flat is this flattest implementation where we're learning with a certain step size. So our first lemma that everything builds on is that this flattest implementation, the lambda max of this case, the flatness, is lower bounded by 1 plus 2 over this, it's kind of a weighted L1 norm of the second derivative of the function. Okay, like the TV norm we saw before. But the difference here, we have this G function. G is a weighting which depends on the data. Okay, so again, it's an integral of the absolute value of the second derivative f times G, and f, the second derivative here is in the weak sense, right? It's a ReLU function, so we get delta. Second derivative of ReLU, so we get delta functions. Okay. So what are the properties of this G function, which is data dependent? It's non-negative. It depends only on the data set. You can get an explicit formula for it. It's just complicated, so I didn't write it here. And it has most of its mass around the center of the distribution. For example, this is, I think, for some uniform distribution, you get this is the G function, meaning it's 0 outside of the distribution support and has this peak in the center. And again, generally it vanishes outside the data distribution, it's 0. So we don't care what happens outside the support of the data. And again, we have this closed form expression for G, but I just don't show it here because it's complicated. And because we know that if we converge to a stable minimum, we have this property that the lambda max is smaller than 2 over the step size. We also know that this stability norm I defined is also smaller than 2 over the step size. Okay, so that's kind of the interesting result here. And why is this important? Because it means that if we converge to a stable solution with SGD of some step size eta, then this stability norm is upper bounded by 1 over the step size minus half. So this is a step size. If we use larger and larger step size, this stability norm will decrease. The function will become smoother. It will have to be to conform to this bound. So this bound we derived under the assumption that we converge to a twice differentiable minimum, meaning the data points do not coincide with the kinks. However, we have analysis in the paper showing the correction in the case you do have some kinks that are coinciding with the data points. Okay, but again, this is in the paper. So now just to simulate to see what we get. So if we have some data point here and we fit them using different learning rates, and here we show the G function we have for this data point, and we will show also the absolute value of the second derivative of the function we have on the left side. So for small learning rate, we get this function which is kind of overfitting, and we see that second derivative in the absolute value is quite high, even though it's a bit lower at the center of distribution, which seems that there's some weighting effect there. And as we increase the step size, we get smaller and smaller second derivative, and the function is kind of smoother. And with higher learning rates, we get much flatter solutions. Okay, so it seems to correspond to the behavior of our bound. And let's look also on the more specific comparison of the bounds, the things we bound. So here we have the x-axis, the step size, and we show 2 over the step size, this line. And if we converge using a one hidden layer ReLU network, we get, because there's this property of edge of stability, you might have heard, this popularized by the paper by Jeremy Cohen, that we get actually the lambda max is sitting almost precisely on this 2 over eta. We sit almost always on this edge of stability after we converge. And if we look at how this lambda max at convergence is different from the lambda max of the flattest implementation, we see there is some gap, even though this gap is very small for the high learning rates. And if we look at our bound, again, we see this bound is lower bounding this flattest implementation, and the bound is actually not bad with the high learning rates. Okay, so at high learning rates, it seems that we get to capture some of the behavior more accurately. Okay, so far I talked about the very simple case of a univariate neural network. What's with multivariate neural networks? So we had this expression, this integral over a second derivative. So what do we get for a multivariate case? So for the R norm you saw maybe previously with the weight decay, you didn't have this G. We get some complicated expression with redundance form. But here actually we can get the more, I don't know, maybe more intuitive expression, which seems like an apt generalization of this. Instead of absolute value of second derivative, we have the absolute value of the Laplacian. And we have this raw function, weighting function, instead of this G, which it has some relations. And again, this is upper bound by the 1 over eta minus half. Again, we call this the stability norm. And we just to get some intuition how it works, so suppose we have some 2D function, right? We have the data points are in blue, and we have the function here in gray. Then we take the Laplacian, we get this delta function, which are the kinks of this function. These are the different delta functions, and each one has different weighting. So this is this part, the absolute value of Laplacian, and we multiply this by this weighting function, which is data dependent. So it looks like this for this data, and then we can calculate the stability norm. Okay, so we can get this exact expression, which is nice. But what can we do with it? So first we can say that, like before, if we use larger step size, then it means the derivative here, the Laplacian, the weighted Laplacian will be smaller, so we get smoother and smoother functions as we increase the step size. And we can also show that if we converge to a stable minimum, we have a stable shallow network, we are not universal approximators, in contrast to standard results, meaning, for example, consider this pyramid function. This is the ReLU over 1 minus the L1 norm of x. Then this function, you can actually implement it precisely using a two hidden layer ReLU net. If you train it with finite step size, there's no problem, you can converge to this ReLU net, you can prove this. And however, if you calculate this stability norm of this function, you find it's infinite. So this means that with one hidden layer, you can't converge to a stable minimum, which is this function. You cannot approximate with any finite step size. So what can we approximate with this stable shower neural network if we can't approximate this function? So it turns out that we can approximate all functions with a certain bounded weighted Sobolev norm. Okay, that is the space of function we can approximate. Okay, so just to summarize this part, we showed that if SGD converges to a stable minimum, then the stable minimum becomes flatter as the step size increases. We must go to a flatter minimum in parameter space. And this flatness in parameter space corresponds to flatness in predictor space, meaning smoother functions. Okay, so that was kind of the message of this part. And this can also lead to better generalization. So it seems intuitive, but can we say more precisely, like what was about generalization? What can we show? So empirically, if we just take this shallow neural network on MNIST, and we check all our bounds, we see the bounds are actually tighter than in the synthetic data case. And if we increase the step size and we go closer to the part where the function is smoother, we actually get improvement in accuracy. Okay, here we use the very large initialization, so it's kind of starting in the kernel regime. So for small step size, the performance is quite bad. So using high step size, you can go far from the kernel regime and get improvement in generalization. Okay, but can we say anything theoretically? So to do so, I just mentioned briefly a result we have from a paper with more Kavya Ravichandran and Nati Cerebro about the implicit bias of step size in linear diagonal neural networks, trying to quantify this generalization performance. So here I'll go to a simpler model to understand the generalization. So this is a very basic, commonly used model. It's a diagonal linear neural network. We have a linear predictor, but the linear predictor is parameterized as some parameter to some power, and we have two parameters so we can represent positive and negative numbers. So this is a very common model to understand implicit bias. And what we show that if we use a similar analysis on this diagonal neural network, we can bound the norm of the predictor we get after optimization in stable minima. We have this weighted norm of the predictor is upper bounded by some 2 over d squared. D is the depth of the network times the step size. So larger step size will cause smaller norm. And specifically, we get this bounded norm which depends on the depth. For d equals 2, and if we assume that the mean of the data is non-zero, which is kind of common, what we get for ReLU at least, the mean is non-zero. Then we imply this bounded weighted L1 norm, which is kind of similar to the rich regime, meaning we're far from the kernel. You can't represent it using a kernel. And in this case, we can show we can get good generalization in a sparse regression setting, similar to previous works on this subject. Specifically, if we just do a simulation on this model, when we sample the x's from the Gaussian distribution with some mean and variance, and label as sparsely generated with the k-sparse predictor from the xn, then what we see is that if we use very small learning rate, this is the curve, the spin curve here, then for small initialization scale, we get the kernel regime, which has bad generalization. Sorry, small initialization of the breed. Sorry, the opposite. Small initialization scale, we get the rich regime, which has, it was proven before to have good generalization. High initialization scale, we get a kernel regime, which has bad generalization in this sparse regression setting. However, when we increase the step size, we see that the generalization improves until at the maximal step size we can use, we're actually close to this rich regime. We have this good behavior in terms of recovering good solutions for generalization, and we can prove that we get a similar generalization behavior as we'd expect with k polylog d over delta, and there's this constant here which depends on the ratio between the variance and the mean of the data. So if the mean here is 0, actually you don't get improvement generalization. This depends on the mean of the data, which is kind of we didn't expect that. It's kind of curious. Okay, so thank you very much for listening. Let me know if you have any questions about the second part or in total.
Any questions for Daniel from the audience?
Hi, a very nice talk. I have a small question regarding the slide with the pyramid function.
Yes.
So maybe you said it and I missed it, but is the result about the fact that you cannot approximate this pyramid function using a neural network trained with gradient descent some step size, or is it actually that no one hidden layer neural network can express this function?
No, just trained using neural network, using a finite step size, and any finite steps you can.
Okay, thanks.
Nice talk. I was just wondering if you had ideas for the multivariate case as well, or other losses, or is this very specific to the setting you described?
You mean in the continual learning case? Did they try other?
Sorry, I mean the implicit bias. I'm sorry, the minimum stability results.
The mean stability. Oh, so we can generalize this to other losses which are like have a unique root, like like quadratic. For classification, you get different. You can get different things, I think. Yeah, because in classification, for example, in separable data, right, you go to infinity, so it's a bit more tricky. What is like how to define minima stability, and is it important? Like essentially, if you train long enough with cross entropy, your gradients will be very small, so you will be stable asymptotically. So it's much more tricky to understand this concept there.
And multivariate, would it be easy to extend, or maybe I missed it?
Was the extension of the multivariate easy, or the extending beyond the multivariate easy? What's the question?
Oh, okay, so I thought maybe I misunderstood, but your results were on f of x. X was one-dimensional, right?
So the first, I had the first part, oh, sorry. First part, where was this? No. First part was on univariate.
Right.
So I derived this result, and then I said in the second paper to be extended to the multivariate case, and that's the result there.
Sorry.
Okay.
Hi, my question pertains to the first part of the talk on forgetting. Given that forgetting can be pretty bad, even in the linear regression case, have you thought about alternative formulations of continual learning? Like, for example, you can maybe store some of the data, some of the models, or a scenario where forgetting isn't as prevalent.
Can you repeat the last part of what is the last word you mentioned?
No.
For example, what? For example, you said something.
For example, let's say you can store like data from the past, or you can store maybe store the weights from like previous.
Yeah, it's a great question. We didn't get to that, but I think it's a great question for a next step you can think of. Yes.
Thank you.
Hi, thanks for the great talk. So in your deep linear model, I forgot, do you have like the bias terms in your?
The linear diagonal models?
Yes.
No, we don't have bias.
Oh, okay. What would happen if you include the bias terms? Is it like does it change it?
Would it change? Yes, I think it would change because it depends on the depth. The depth is changing. Actually, it's curious. Like, it's kind of in contrast to previous results, and the previous implicit bias results for small initialization showed that as you go deeper, you get higher sparsity. Like we saw one talk here that you have 2 over L norm, right? It's closer to the L0 norm. And this is what happens with higher depth, you get better sparsity. However, if you use high learning rate, you get the opposite. You go from L1 to L2. Like you get worse and worse in sparsity if you use high learning rates in deep models. So yeah, it's kind of curious what's going on there. And I guess if you add bias or do some non-homogeneous model, it will be different, right? For each component, you will have different behavior because it's diagonal, so it's separate for each component.
I see. And another question, is this stability norm for the multivariate part, is this like an upper bound on the R norm, or is it at all related or not?
Is it upper bound on the R norm? I don't. Maybe I don't see why, but if you can prove it, maybe it would be nice.
Okay.
All right. If there's no further questions, let's thank Daniel once more.
Thank you.